4.6 Representing thermochemical cycles. You can use enthalpy diagrams rather than thermochemical cycles to represent the enthalpy changes in chemical reactions. These show the energy, enthalpy, levels of the reactants and products of a chemical reaction on a vertical scale so you can compare their energies. If a substance is of lower energy than another, you say it is energetically more stable. So far, you have considered enthalpy changes, not absolute values. When drawing enthalpy diagrams, you need a zero to work from. You can then give absolute numbers to the enthalpies of different substances. The enthalpies of all elements in their standard states, i.e. the state in which they exist at 298 Kelvin and 100 kilopascals, are taken as zero. This convention means that the standard state of hydrogen, for example, is H2 and not H, because hydrogen exists as H2 at room temperature and pressure. Pure carbon can exist in a number of forms at room temperature, including graphite, diamond, and Buckminster fullerene, buckyballs. These are called allotropes. Graphite is the most stable of these and is taken as the standard state of carbon. It is given the special state symbol, brackets S, graphite, brackets closed. So C, S, graphite, represents graphite. Here are two examples of reactions with their enthalpy changes represented both as thermochemical cycles and as enthalpy diagrams. Example number 1. What is the delta H for the change from methoxymethane to ethanol? The standard molar enthalpy changes of formation of the two compounds are CH3OCH3 has the enthalpy change of formation of minus 184 kilojoules per mole, and C2H5OH delta FH is equal to minus 277 kilojoules per mole. If you were to do this using a thermochemical cycle, first of all, you would write an equation for the reaction. Then, write down the elements in the two compounds with the correct quantities of each. Thirdly, put in the delta FH values with arrows showing the direction from elements to compounds. 4. Put in the arrows to go from starting materials to products via the elements. 5. Reverse the sign of delta H if the red arrow is in the opposite direction to the black arrow. 6. Go round the cycle in the direction of the red arrows and add up the delta H values as you go. If you were to do this using an enthalpy diagram, first of all, you would draw a line at level 0 to represent the elements. You would look up then the values of delta FH for each compound and enter these onto the enthalpy diagrams, taking account of these signs. Negative values are below 0, positive values are above. Thirdly, you would find the difference in levels between the two compounds. This represents the difference in their enthalpies. 4. Delta H is the difference in levels taking account of the direction of change. Up is positive and down is negative. From methoxymethane to ethanol is down, so the sign is negative. From ethanol to methoxymethane, the sign is delta H would be positive. Notice how the enthalpy level diagram makes it much clearer than the thermochemical cycle that ethanol has less energy than methoxymethane. This means that it is more energetically stable compound. The values of delta H for the reaction are the same whichever method you use. Example number 2. To find delta H for the reaction NH3 plus HCl equals NH4Cl. The standard molar enthalpy changes of formation of the compounds are NH3 delta FH equals minus 46 kilojoules per mole. For HCl, the delta FH equals minus 92 kilojoules per mole. And for NH4Cl, it is minus 314 kilojoules per mole. If you were to do this using a thermochemical cycle, you would write an equation for the reaction, write down the elements that make up the two compounds with the correct quantities of each. You would put in the delta H values with arrows showing the direction, that is, from elements to compounds. You'd put in the arrows going from the starting materials to products via the elements. You would reverse the sign of delta FH if the red arrow is in the opposite direction to the black arrow. And finally, you would go round the cycle in the direction of the red arrows and add up the values of delta H as you go.